Okay, so maybe we'll get going again so we can get to lunchtime. I'm sure people are getting hungry. This second session, kind of loosely titled Closing the Gap, and as I mentioned, really what we're interested in exploring is how the use of computational design and manufacturing tools are changing practice from some first-hand experience. The first two speakers we have from our partners Bureau Happold and Arab, they'll discuss how they're going to discuss how established disciplinary boundaries are shifting and their experience of it. And then secondly, we'll move on to Fabian and Ben, who are really kind of representative of a new kind of profession that's emerging, that's dealing with this complex space between information management and digital manufacturing and production. So the first speaker we have is Wolf Mangelsdorf, who's a partner in Arab, or sorry, in Bureau Happold. Partner in Bureau Happold. And also involved here in the school, both with the IG and the MTech program, where he has been teaching for a number of years. Wolf was born and grew up in Germany near Würzburg. He studied architecture and civil engineering in Karlsruhe University, where he also worked for an architectural practice for a period after graduation. After a research stay in Kyoto University, he moved to Britain in 1997 and became a design engineer at Anthony Hunt Associates, who are another consulting engineering practice in London. Since 2002, he's been with Bureau Happold in London, where he joined as an associate and project leader for a number of years, and worked on projects such as the Battersea Power Station and the Museum of Transport in Glasgow. He's now a director and partner in Bureau Happold, and he leads the dynamic structures team, whose portfolio of work is diverse, including significant landmarks, projects, and with signature architects in buildings that include educational buildings and also have a specialist focus on refurbishment and conservation. The range of projects extends from small bespoke projects to large urban regeneration schemes. So please welcome Wolf Mangelsdorf.
Cool. Thank you. Well, closing the gap was the theme, and what I want to talk about is, I'm a structural engineer. I want to, primarily from the structural engineer's point of view, talk about how we involve the tools that allow us to develop complexity in our designs, from design all the way to construction. And I want to start with that, how things have developed, because it's a bit of a timeline thing. So I want to go back to the mid-90s, Gateshead, Sage Music Center, sort of complex geometry type thing. Yeah, it's based on a torus geometry, and we started very early to develop this as a computer model, which then was used as a setting out model by the architect, but also as a setting out model by the contractor. And we're already in an interesting territory, because setting out is architect's business normally, and with these kind of complex structures where the structure, the skeleton of the building defines the envelope and the outline of the envelope, there's a shift of this responsibility towards the structural engineer, and that is sort of one of the questions I need to ask later on. But we parked this for a moment. But the tools were simple, yeah. It was centerline models that were issued, and then the contractor takes this on and develop their thing on top of it, and that's sort of what it looks like in the end. Moving on, British Museum, also similar time frame, a little bit more sophisticated here, because the connection between the contractor and us, you know, the fabricator and us as the engineers, was even tighter, because the geometry and the fabrication technique are so totally interwoven, so much so that we actually had a pre-tender workshop with a number of contractors to develop what construction methodology would be the right one for this particular roof, and then developed it further. Another interesting question: where do we cut it off? Where do we cut off design and then move into the space of the contractor and involve the fabricator? So here we went all the way from our mathematical models of the roof, which were, you know, reconciling something that is actually bulging with something that is round in the middle and square all around it, done by hand. Probably today it would be a couple of sliders on the grasshopper model, I suppose. But here we go, and that all went all the way to robot manufacturing, automated welding of the joints and cutting of the joints. I always think that the Smithsonian Institution in Washington, D.C., which is also a Foster's project, is sort of the natural successor in the development to the British Museum, and because it's a structure that is very similar in its geometry, but or in its makeup, but it's actually not triangulated. So it has a little bit more complexity in the structure. It's not that clearly sort of a shell thing, but still the geometry is quite an important part of it, and the manufacture even more complex than the British Museum. Yeah. So here we used a Tekla model, which is a fabricator's tool. Tekla is a fabrication. Or it's a CAD tool that's used by the fabricators to actually prepare the information that would then be taken on, but it would still be heavily manipulated by those who build it, because the traditional thing is that we define the geometry, we define the member sizes of our structure, and then the manufacturer designs or does the calculation of the connections. Yeah, the connection design is a vital part of it. We do have our thoughts about it, but very often, and I have another example about this a little later, very often these kind of connection designs are very much driven by the ability of the contractor, by their erection methodology, and a number of other factors which we don't know immediately. So an area of overlap where the work of the manufacturer and the work of our team, our design team, integrated with the architect, needs to be very much aligned and intertwined. And it looks good, yeah, I must say, very elegant. So, Glasgow Museum of Transport, you see it took a long time to get it off the ground. Yeah, 2004 we won the competition, 2011 it was actually inaugurated. The complex geometry was actually developed by Zahadid at one end, using eventually digital projects, yeah, but going through all the loops, using Rhino, using hand-drawn, using whatever. And at our end, going from Rhino all the way to Revit. But what actually came out of it to manufacture this thing here, which is, as you can see, in its whole setup highly complex, was something that needed to be a little bit more involved, because here 3 strands come together quite significantly. It's the architect, or 4 actually. It's the architect's idea of the envelope into which this structure has to disappear, so we don't see it. Yeah, it's not like the Smithsonian Museum or the institution or the British Museum, where the structure is the architecture. Here, the structure has to disappear. A completely different challenge. Not one I actually quite like. Yeah, people always ask me, "Aren't you sad that you don't see it?" No, it's so ugly. I don't want to see it. Yeah, it's here to support the envelope. Yeah, it's very utilitarian. Believe me, it really is. Yeah, standard section and so on. So we have got the architect's work. We've got our structural design setting out work. Yeah, because that all has to fit. It has to work equally then with the analysis, because it should stand up in the end. It's part of our job, and in the end we have to erect it. And a structure like this, where you can't have a scaffold everywhere and then just drop it, has to be erected in a sequence that needs to be developed. All these kind of steps are totally interlinked and intertwined, and require a modeling that is taken much further than just having a drawing and slapping it on the contractor's desk. Yeah, and here we go. This was the involved kind of modeling of the construction sequence, totally linked to our analysis model. Everything scripted in between. Yeah, everything had to be linked through little Excel sheets. I call it scripts. Yeah, it's not really scripts. It's just data exchange. Yeah, because we're using the different tools. We're using the different analysis and drawing and what have you tools to at their optimum. We use the right tool for the right task. That means they're not necessarily compatible. We have to bring them together and make them talk to each other. That's very simple, because they actually only work with 3 or 4 types of data. It's nodal point and geometry, and it's forces and loadings. So if we can reconcile those, it's just how they spit it out and read it back in, which is the difficulty of difficulty at times. Excel can do that for you. So here we go. We went through an elaborate construction sequence, both in analysis terms and in terms of drawing this and developing this with the contractor. And that doesn't happen without the discussion with the contractor and knowing that the manufacturer actually also plugs into the same set of tools in a very similar way. And to facilitate this, we drew it again in Tekla. Yeah? We used their tools, their types of tools to draw the structure so that they could finalize the design of the connections. And you see what does connections look like. Yeah? Nothing like what we actually had envisaged, because they found that these canned connections, as we call them, I have this thing here, these canned connections here, which are basically cylinders around which we weld all the bits and pieces that then connect to the rest, are the easiest way to do it. Brutally ugly, but highly efficient, because all the complexity is taken away from the site. It's all happening in the workshop. You can set it up vertically, plug all your bits in, welding torch, job done, and all you put together is a little kit of parts on site. And I had never more than about 5 people there. Yeah? It's the same contractor who built the Olympic Stadium now with us, and they had 20 people to build the entire Olympic Stadium, 25 or something. Yeah. So because of that pre-manufacture type thing, we're able to minimize the complexity on site, and that's a highly involved process, not just in terms of modeling, but also in terms of talking, I would think. Yeah. I should mention in this case that the other types, they were just roofs. No, this isn't just a roof. It's a museum, and the museum has a backload of M&E, air supply and air conditioning and so on running with it. And you know Zaha Hadid, you wouldn't want to see a duct running somewhere, so that had to be hidden as well. And that's similarly sort of the modeling task the coordination task that has to go along with it. So at that point, the package changes and it becomes a Revit modeling exercise where you can fit all these different things in. Yeah, again, another tool for the task put together and then used for information supply. I've got another structure here which sort of shows maybe a little more how the complexity of a visible structure can actually pose some interesting challenges, but how you can actually get it working right from the beginning. This is some of you may have seen this, yeah, in other talks I've given. The Media Cité in Liège project with Ron Arad, the little roof. That's what it looks like on Ron Arad's sketches. And the architectural group with Ron Arad, they have the done a picture? Good. They have done their best to translate this then into a scheme that not only reacts to quite diverse site conditions, but actually allows us to model it parametrically from the beginning. Now here, that was the good bit and the bad bit, because I talked about the models, yeah, being done in the right tools for the task. Here the right tool for the task in the way the architects work, and work in this fluidity of translating the sketch into something that is manipulated on the computer parametrically. That sort of thing was best done in Maya. Now, those of you who work with Maya know that it's an absolute pig when you translate it into structural center lines, because it doesn't work like that. So we had to go through loops and loops of back scripting to actually translate the one into the other. Maybe that's because it was 2006. Maybe today you would do it slightly differently as well. But interestingly, as tools develop, it becomes easier. The thinking has to be the same somehow. Yeah, the thinking, if it's not there, it just doesn't work. But what was interesting here is that this process, we arrived eventually at a Rhino model which was much easier to control, but it didn't have that fluidity in it anymore. What it helped us do is actually directly link into what the manufacturer was able to produce and able to model themselves. And they were excellent. The manufacturers were absolutely capable of taking our geometry, understand it, and then translate it into their models, including all the design and calculations of the connections that are necessary. I say they were excellent. Yes, they were, but the limitations of their software was again throwing up a little bit of a different challenge, because we had curves everywhere. Everything was smooth curves. Their program does only straight lines, so we have to translate everything through a script from straight line, from curves into straight lines. So any kind of curved beam, you can see that the model printout at the top is faceted. Facets from 10 millimeters to 100 millimeters. Once the flame cutter cuts the material, you don't see the corners anymore, so nothing looks jagged edge or faceted, but we have to go through this, and without us actually being able to script this bit, it wouldn't have been possible. That's what it looks like. That's what it looked like during construction. And then the last model I want to, or the last example I want to show you is the Yale School of Management, which we're just currently building in, well, Yale. It's a project with Foster and Partners. And what's interesting here is not so much the complexity of the geometry, there isn't much of it, but that we built this completely in the computer. Everything was done in BIM, yeah, call it BIM. It's Revit, yeah. So we built it all the MEP is done in Revit, but all the structure is done in Revit as well. And we're using not just Revit, but we're also using a fabrication model, again using this other package called Tekla, which allowed us to take on a package which is normally, as I said so many times now, outside our scope of works, the design of the connections. Again, they're not exactly beauties, but there are functional connections, exactly the right thing for this type of building. But we could take on this piece of work for the contractor, did all the modeling, and it fit straight into their little computer screens there on the fabrication machinery, and everything was computerized manufacturing. Yeah? Nothing was actually then double-handled or triple-handled. The interface was really moved all the way from designer does design, contractor does fabrication drawing with everything comes with it, to designer does everything to fabrication drawings. It was well paid, and that then rewards you for the extra bit of responsibility and liability you take on, and it made everything quite smooth. Yeah. So I think there is a bit of a model for the future here, in many ways. Yeah. So I tried to cast all the things I said sort of in diagrams, yeah, and that's so bear with me, yeah. How do we work? Yeah, the integration of the design team and the fabricator team. This is the theme here. At present, it's a bit of a mess, yeah. So if you're unlucky, you've got 3-4 different models: one for the facade engineer, one for the MEP engineer, one for the architect, one for the structural engineer, and then various different contractors and fabricators that all work with their different models. Or if you're unlucky, they don't even have models, so they need 2D drawings. Yeah. So that's one of the sort of standard ways of doing things. Yeah. If you're lucky and you work with a multidisciplinary engineering firm, I should say at this point, no, you can get an integrated 3D engineering model. There is benefits to that, yeah? That you can actually bring it all together in one model, like we saw for the Yale School of Management. We can model the MEP and the structure together, the facade in the same package. It's still, in most cases, has a separate architectural model which runs on a different sort of time scale maybe or whatever. But very often, yeah, they're very close. Yeah, then you can link directly into the fabricator models. Yeah, with much more direct streams, like we did for Media CT, for example. Yeah, you still have some bits that have to be done in 2D drawings, but then that's not that much of a problem. And ideally, yeah, that's sort of where we're trying to get to, yeah, that we have an integrated architecture and engineering model. Throws up the big question: who is responsible? Yeah, who takes on the responsibility for what kind of platform do we? And I would like to throw that back to you as the audience to see what your views are on this. Yeah, or, you know, going in here and actually taking on some of the bits of the fabrication. Yeah, I go back to that this could work either with a separated architects and engineers model or with an integrated model. This is the Yale thing. Yeah, we took on the modeling of the connections here. Then we've got Fabian and his group. They sit in here as well. Yeah. Specialists that take on those tasks, that are the translators, so to speak, between the architect's or engineer's intention, design performance specification, whatever you want to call it, and the actual translation of that into the physical artifact. Yeah, and that works with this kind of thing as well. I don't know if you ever get there, complete integration or partial integration of the fabrication model, but we will see. And there's still room for those very specialist bits that we will hear about a little later. Because I've mentioned all this because what we need to bear in mind is we are not this, yeah? We are not, very often we talk about the sort of technology transfer from the aviation industry or the shipbuilding industry, and there's one big flaw in that, in that model, in that idea. And that is that Dassault, they do it all themselves. Yeah, they have one massive platform where they do a digital virtual prototype of an airplane that never flies until they build the first one. They model it down to the level of detail you see here. Yeah, they model the block that actually puts the screw into the hole, because if the hole isn't big enough, the whole thing can't be assembled, and you don't want to go back and redesign it. Yeah, so that's not what we really do, yeah? It's also, for various reasons. One is the teams are much more diverse, and the teams, in my view, are becoming more diverse. The number of specialists we're getting on our projects is becoming bigger and bigger and bigger rather than smaller. So we need to develop environments where we can collaborate much more freely and interchange information much more freely, and rather than trying to unify them. You know? The other thing is that also our supply chain works completely differently, because we as the designer, we are not in charge of our the supply chain or the manufacturers. There's a tendering process that sits between us, between those two things, that needs to be sort of recognized. Yeah. So this kind of thing, all integrated. I don't even think we want to go there, but we need to be careful that we don't aspire to this, because I don't think it's realistic. So where do we want to go? Yeah. These are my sort of initial questions. Some of them I've already asked. Yeah. Time, cost, quantity, who is actually benefiting from it? Is it us? Is it the quality of our product? Is it our clients? Yeah, and eventually, yeah, who pays for all this? Yeah, so do we get a bit more money for our design, or can we offset the gains that we get from smoother, faster design by getting maybe a little bit more fee? I don't want to even go there. Yeah, what are the expectations that our clients have for us? What are our own expectations? Yeah, what are we doing it for? Will the manufacturing and the design move closer together? If they do that, yeah, we had a discussion before the event here in the little breakout room. There's a tendency for the manufacturing to become much more determining in what we're doing, and the manufacturers having their own systems and having their own kind of construction methodologies that have a direct impact on how we do things. So take the Glasgow example. It would have been just a waste of time for me to design all the connections, because the contractor came back, they had their own idea which actually linked into their way of manufacturing and way of working. So if we want to get the efficiencies out of this, we're moving the two things closer together. That means we're tendering earlier, we're bringing our manufacturers in earlier, but where's the cutoff point? Where do we actually step over the line where it becomes not tendered but negotiated? And what is the benefit? Where does the competitive element lie? Yeah? That sort of similarly links into the next question: how do we manage the supply chain and the value chain? And the last question, really the most important one, is it the relationships in our industry that drive the process, or is it our tools, or is it both? So who is in the driving seat here? Thank you.
Thank you, Wolf. Now we're going to hear from